Hello, so what we're going to do today in today's video is differentiate the arcsec function. So arcsec just means the inverse sec function. And if we remember from a previous video, so sec of x is just the same as 1 over cos of x. So we want to differentiate the inverse sec function in this video. And similarly to how we differentiated the inverse cosec function, so the inverse the inverse cosec function, we've got to be careful with this derivative. So we're going to have to analyze the graph and analyze what type of function we have here with this arcsec function. So is it going to be an increasing function? Is it going to be a decreasing function? And in either case, that means the derivative is either going to be positive or negative for all values of x in our domain. So we got to check that before we actually do the calculus and algebra and work out a function for the derivative. So what we can do then is we can start off just by a sketch of y equals cos of x. So y equals cos of x. So it looks something like this. So something like that. And what we notice is that, okay, we've got 0 there. We've got pi over 2 there. We've got pi there. And then we've got minus pi over 2 there, and so on and so on. So what you'll notice is that from this like minus pi over 2 to this pi set of values, we've got a many to one function. So when we want an inverse function defined, we can't have a many to one function. We've got to have an injective one-to-one function. And the injective region of this function of cos is this region here. So between 0 and pi. So if we restrict the domain between 0 and pi, well, we just get a one-to-one function. So just using the line test, the horizontal line test, we just get one-to-one mappings, so a one-to-one function. So that's what we want. So we know that our domain has to be between 0 and pi in order for there to be an inverse cos function. And in order for there to be an inverse sec function, we also have to restrict the domain of the sec function between 0 and pi using this same logic here. Okay, so what we can now do is try to sketch a graph of sec. So y equals sec x. So remember, sec is just 1 over cos. So just by picking out some key cos values from this cos graph, what we can tell is that if we plug in 1 over 1, for example, so cos of 0 is 1. So 1 divided by 1 is going to give us 1. So therefore, when x is 0, we're going to get a sec value of 1 there. Okay, so now let's go to pi over 2, which is, let's just say, over there. So pi over 2 is there. So as x increases to pi over 2, well, what happens to cos? Well, cos decreases. So as x goes closer and closer to pi over 2, the cos function decreases and gets closer and closer to 0. So that means 1 divided by a number getting closer and closer to 0. Well, that's going to tend to infinity. So you're going to kind of get something like this, which goes up like that. And you're going to get an asymptote at this pi over 2 value, because cos of pi over 2 is 0 and 1 divided by 0 is undefined for this sec function. Okay, great. So now we can go to this pi over 2 part of the domain to this pi part of the domain, and a similar kind of logic. So when x is pi, well, cos pi is -1. So 1 over cos pi is going to be -1 itself. So we can just put in a -1 there, and that's 1 up there. So we got that there. And again, when we go from pi to pi over 2, so when we go backwards from pi to pi over 2, what happens? Well, cos gets bigger, or the magnitude of cos gets smaller. So when you divide 1 by a number which has a magnitude getting smaller and smaller, well, it's going to tend to negative infinity. So it's going to do something like this, the sec graph. And again, it won't touch the pi over 2 asymptote, because cos of pi over 2 is 0 and 1 divided by 0 is not defined. So a sec graph kind of looks something like this on this restricted domain. So now we can just kind of use this to draw to try and draw an arcsec function. So remember, we can draw inverse functions by kind of using this y equals x mirror line. So this is the line y equals x. So y equals x. So we just want to reflect the black graph over this y equals x mirror line. And if we do that, I mean, it's quite hard to see from just this diagram, but if we were to do that, we should get something that looks like this. Let me just make a note that this is y equals arcsec of x. So that's what this graph down here will be. And yeah, so if we do that, well, if we look here, we've got a coordinate of 0 and 1. So the arcsec coordinate there is going to correspond to a 1 and 0. So we've got a 1 and 0 there. If we take this coordinate there and reflect it, so this is a pi minus 1 coordinate. So the reflected coordinate is going to be a minus 1 pi coordinate. So minus 1 there and pi, let's just put pi up there. So we can have one coordinate there, one coordinate there. And yeah, so if we reflect these graphs, we should get something that looks kind of something like this. So doing that there, sorry, my bad, this shouldn't be going so high. We've got an asymptote of pi over 2 on the x-axis with the sec function. So that means the arcsec function must have an asymptote of y equals pi over 2. So let's just make that clear. We've got an asymptote there. And so, yeah, so the reflected graph kind of does something like this, and it does something like that on that side. Okay, so yeah, I mean, it's not a very good sketch, but that's a rough sketch of what arcsec, the graph of arcsec looks like. And similarly to the previous video, what do we notice about these gradients? Well, when x is in this part of the domain, so the domain from 1 up to infinity, well, we get a positive gradient on this function. And the same thing over here. So these gradients here are all positive again. So when x is between minus infinity and minus 1, again, we get positive gradients. So what we can conclude from this sketch is that therefore d by dx of arcsec of x must be greater than 0. And that is a fact that we've got to bear in mind when we calculate this derivative. It must be a greater function than 0 for all values of x in the domain. I mean, let's just make a big point of this. So d by dx of arcsec of x is greater than 0 for every value of x in the domain. And this is our domain here. So from minus infinity to minus 1, and from 1 up to infinity. So that's the key thing we need to bear in mind. So now we can just do the algebra. So if we let y be equal to arcsec of x, so again, just using the same process we've always used with these kind of derivatives. So apply sec to both sides. We're going to get sec y equals x. Differentiate both sides with respect to x. We're going to get d by dx of sec y equals d by dx of x. And we know that d by dx of x is just the number 1, because dx over dx is just 1. And now we can use some chain rule to differentiate this sec y. So when we differentiate with respect to x sec y, so we've got a function of x, because y is a function of x. As we know from here, y is a function of x, namely arcsec of x. So we can just use the chain rule. And our chain rule says that the function inside the sec function, if we take that derivative with respect to x and multiply that by the derivative of sec of that function with respect to that function, that will be our derivative, our initial derivative. And so just by simplifying this, we get dy by dx multiplied by the derivative of sec. Now, from a previous video, we know that when we differentiate sec, we should just get sec times tan. So sec y times tan y. So we know that when we differentiate this function with respect to x, we get this there, so dy by dx times sec y times tan y. So what we can therefore do, going back to this previous slide, is say that 1 must be equal to dy by dx times sec y times tan y. Okay, great. So now we can just divide both sides by this sec y tan y. And if we do that, we get dy by dx equals 1 over sec y tan y. So in other words, when we differentiate arc sec of x with respect to x, we get 1 over sec y times tan y. But again, we've got, well, we want to differentiate a function of x, but we've got an answer which is a function of y. So we've got to get rid of these, this function of y on the right-hand side. But what do we know? Well, we know that sec y is x. So let's just plug that in. So this is equal to 1 over x times tan y. And then we got this tan y that we want to get rid of. So we're going to have to use a trig identity to do that. Okay, so we know from trig identities that 1 plus tan squared y equals to sec squared y. And remember from the previous slide that x equals sec of y. And we know that from this bit there. So therefore, this means sec squared is going to be x. So you've got x squared, I should say. So x squared there, and a 1 plus tan squared of y there. If we just make tan the subject of the formula, so therefore we get tan y equals the square root of x squared minus 1. So we can just plug this result down there into our formula up here. And if we do that, we'll get 1 over x times the square root of x squared minus 1. And this is for x values in our domain, and our domain was negative infinity to negative 1, union with 1 up to infinity. Okay, so again, similarly with the previous couple of videos when we differentiated arc cosec, we need to check, is this result greater than 1 for all values of x in our domain? Because remember, it must be true, this result. This must be true. The derivative must be greater than 0 because the gradient of this graph, this arcsec graph, is always greater than 1 for x values in the domain. So we've got to do some analysis and check, is this function bigger than 0 for all of these x values here? Okay, so what do we have then? So, the question is 1 over x times x squared minus 1 greater than 0 for all x values in our domain? Well, again, yeah, let's just check. So let x be in the smaller part of the domain. So let's just say from negative infinity up to negative 1. So we'll call this case number 1. So what do we have then? Well, if this is true, well, x must be less than 1. So x is a negative number. Okay, that's fine. We know this numerator of 1 is always going to be positive. So that's fine. So if you've got a positive number divided by a positive number, that's going to be a positive number. So because of this positive number on the top, we need this denominator to be positive. So we need this x times x squared minus 1 to be greater than 0. That's what we need in order for us to have a positive derivative. Okay, so if x is in this negative region of the domain, well, we're going to get a negative x value. So therefore, we need the square root of x squared minus 1 to be negative as well. However, if we look at this identity here, so we know that tan y equals the square root of x squared minus 1. And we know that x is in this domain here. Okay, so when you do x squared for x values in this domain there, well, you're going to get a number bigger than 1 because the magnitude of x is bigger than 1. So when you square a number bigger than 1, or with a magnitude bigger than 1, you're going to get a number bigger than 1. So we know that. So therefore, x squared minus 1 must be bigger than 0. And therefore, if we just square root that, the square root of x squared minus 1 must also be bigger than 0. But we need it to be less than 0. So this doesn't quite work. So the only way we're going to make this work is if we make this an absolute value. So we can't change this part of the function there because this is always going to be greater than 0 in this part of the domain. But we can change this x there and put a modulus there just to make sure that we get a denominator which gets us a positive value for all values of x in the domain. So therefore, what we can now say is that so for all values of x in the negative part of the domain, we know that the derivative of the arcsec function is going to be 1 over the modulus of x squared minus 1. Now we can also consider this second part of the domain as well. So let x be in the positive part of the domain, so from 1 to infinity. Well, I mean, when x is in this domain, again, the modulus of x is also going to be bigger than 1. And we also know as well that x squared minus 1 is bigger than 0 because we just showed that up there. So again, what you're going to get is you're going to get a positive denominator there. So a positive numerator divided by a positive denominator gets you the positive number that we're looking for. So therefore, this derivative works. So therefore, in conclusion, what we know is that when we differentiate the arcsec of x function, we get 1 over the modulus of x multiplied by the square root of x squared minus 1. And that is the final result for this video.